Hello, my name is Bala Sundaram. I'm the chair of the physics department here at UMass Boston, and I'm here to tell you a little bit about a project that I worked on a few years ago. It is an interesting application of molecular dynamics simulations, and it comes in a context where these ideas actually play a very big role, and that is with these wonderfully complex things called colloidal suspensions. So the title of my talk doesn't say that quite so clearly. It's a little more convoluted. It says field-induced phases in a heterogeneous mixture of charges. And that mouthful, as I hope to tell you, is actually quite a simple idea. And all it is a bunch of charges interacting with each other and producing unusual behavior. So the starting point, the way the talk is laid out, is that there are three parts to the talk. The first part is simply a motivation, which is going to tell you a little bit about why these objects, colloids, are interesting, in particular if you put them in an external field. I'm going to deal with a specific experiment that came out in 2005, which dealt with something called anomalous orientation. I'll explain to you what that means. And that's going to provide, the findings of that experiment are going to provide the foundation for the model that I will construct. And that is what I refer to as a dynamical model. In the context of the molecular dynamics MOOC that you've gone through, dynamical model simply refers to the fact that we're not dealing with a equilibrium or a thermodynamic situation. We're actually dealing with a situation where things are actually changing with time. They haven't quite settled down. So that's the interest. And then I finally get to the results and a discussion of what they mean. So we start with the idea of colloids in external fields and charged colloids. So what does all that mean? Colloids are very interesting. They're basically objects which are suspended in another object. It could be a liquid suspended in another liquid, a gas suspended in a liquid suspended in a gas, a solid suspended in a gas, etc. And possibly the most simple example, or the most common example, is milk. It's an example of a colloid. It's a special type of colloid called an emulsified colloid, but those are just subcategories. So that's an example of a colloid. Quite often these colloids are in fact charged, meaning that they carry either a positive or negative charge, and depending on their charge they can attract or repel each other, and they can form fairly interesting complex structures, especially when you put them in the presence of external fields. In this case we're going to be talking about electric fields. Now, of these phenomena, and these phenomena are collectively referred to as electrokinetic. Kinetic meaning it's got to do with the motion of the charges, and electro has to do with electrostatic repulsion or electrostatic interactions. Very, very small subset of these problems are clearly understood. We have, there's been extensive studies, and quite a number of these phenomena have been well studied, but I wouldn't say fundamentally there are a large number of outstanding questions. Now, life gets a little more complicated where instead of having just simple round colloids, they get structure. For example, they could be in the form of a rod. So like my pointer over here. Now this would be an example of a colloid where there's a shape, and it can do all sorts of things. It can spin around, and depending on which end the charge is, when you put an electric field, it can flip around and do all sorts of things. You mix and match these, and you get a very, very interesting and novel behavior. And so the motivation for this particular work that I'm going to tell you about were the results of an experiment done by Mantegazza et al., and it appeared in Nature Physics in 2005. And one of the things that they did was they took colloids shaped like this, rods, and they mixed them with little round colloids. And they put in an electric field, and in the process they saw some very, very interesting novel effects. And so let's start by I'll showing you a little bit of the results that they found. So, and that is what is called this phenomena of anomalous orientation. So this was the experimental setup. They took dilute suspensions, which means that there are very few particles relative to the amount of the stuff they're suspended in. And these are what we're going to call primary particles. And these primary particles, as far as whenever I say primary particles or whenever you see primary particles, you should really think of things like the pointer, like the rod. And they are in the neighborhood, they're surrounded by these smaller secondary particles, which are round. They don't have this profile. They're much smaller and they're rounder. And all these objects, all these charged objects, are placed between two plates where there's an AC electric field. And the AC electric field basically means that the polarity keeps switching, goes positive, negative, negative, positive, so on. Under these circumstances, you get this very interesting effect, which is called electrically induced optical birefringence. Now, what does that mean? The electrically induced means it's a consequence of the electric field that you put on. The optical means that you can see this phenomena by shining light on it. And the birefringence basically means that if you look at it in one direction as opposed to another direction, the refractive index is different, which means the amount that the light bends is different depending on which direction you look at it. So that's what all that means. And so what they did was they took this box with these two different types of colloids, they shone light on it, and they actually measured what they could see in one direction as opposed to shining light and looking at it from another direction. And in quantifying this, they actually calculated this thing called the Kerr coefficient. And the Kerr coefficient is nothing but, it's something which tells you how the change in the refractive index between the two orientations depends with respect to the square of the electric field. Now, this particular effect depends on the square of the electric field. Lambda is the wavelength of the light that you're using, and this B depends on the frequency of the AC field. So if you change the AC field, change the frequency of the AC field, then this quantity B changes. And B changing basically means that for the same field value and the same wavelength, the change in the refractive index could be different. So they study that, and we'll see what that allows you to do. And in the process of doing this, they use different types of these rod polymers or primary particles, and they used a range of secondary particles. And the interesting thing was, in each one of these cases, they did see this effect of anomalous orientation. So what is this mysterious anomalous orientation? So let's go to a schematic. So before we get there, a couple of things to note. If I just had the primary particles, so if I just had just the rods, and I put on a AC field, as long as the AC field was not too slow, the rods would point and switch alignment depending on as the field changed. So as the field changes polarity from positive to negative, the rods would rotate around. So that is what we call normal orientation, meaning that these particles line up with the electric field. If instead you just had the tiny round ones, since they don't have this preferred orientation, they just go all over the place. So there's what is called isotropic behavior. That means if you sat in the fluid and looked around anywhere, you would see the same amount of concentration of the small particles. When you put both of them together, the rods as well as the round particles, that's when you get anomalous orientation. So schematically, let's just recap. If we just had the primary particles, they line up with the field. So here you can see that these blue rods are lining up with the field. If I had the round particles, the secondary particles, which are described as the pink dots, if I just had those, they would just be in some pattern. Well, no pattern, I'm sorry, just distributed almost homogeneously. If you put them both together, there's some frequencies, some range of frequencies and some range of field strengths for which they line up just like they did before. So here you can see, with or without the secondary particles, they have the same behavior. However, the interesting part of the anomalous orientation is when you see this, which is the field is pointing this way. This is where it wants to line up. And the rods actually line up in a direction that's perpendicular. And so the orientation is anomalous, meaning it's actually doing something which it's not supposed to do. Why isn't it supposed to do this? Because energetically, this is the much more comfortable state to be in. This costs more energetically, and so this is not something you'd normally expect them to do. So here's the schematic, and this is the picture that I'd like you to keep in your mind as we continue talking about this in terms of the quantitative measure, which is the Kerr coefficient. So in terms of the Kerr coefficient, this is what you get. When you've got just the primary particle, just the rod, and you notice here what we're changing up here is the frequency of the AC field. So as you change the frequency of the AC field, as the AC field the frequency goes up, which means it changes direction faster, you see that the rods go from a situation where they go from a positive value, and positive value basically means that they align the way they're supposed to be. And when it gets to high frequency, you get an effect where if the field is switching around too much, these things, it's too fast for these things to respond, and they just basically stay where they are. So that's what this says. If you just had the small particles, the round ones, then you see no special effects. Let me go back to where I was. So here you see no special effect, meaning that there's no preferred orientation at all. Now you get this anomalous case. In the anomalous case, you notice that this B value is negative. And it's negative for a range of frequencies. And so you can see that there's negative for a range of low frequencies. So for the low frequencies, you see from here to here, the value is negative, which means that you have an orientation like this, the anomalous. As you continue increasing the frequency, it becomes positive, in which case you go back to normal orientation. So it's normal orientation over here, and anomalous orientation over here. And then when the frequency gets too high, it doesn't respond again. So the lesson to be learned from this quantitative measure is when this value B is negative, then you think of it pointing in the counterintuitive direction, whereas when it's positive, then it's pointing in the usual intuitive direction. Now, using this measure, now that we understand how to interpret it, they did several things. So let's take a look at A first. So this is one where they kept the round colloids, the small ones, the same, but they used a variety, 4 different types of rod. And you can see for each one, it doesn't matter which one it is. Notice that the first one, the green one, is E. coli. So it's the E. coli bacteria. And so the bacterium actually is a colloid. So it has charges that run up and down, behaves exactly like a rod. And there you can see there's a small range of frequencies for which it's negative, meaning it points anomalously, counterintuitively. And then it increases. As you increase, it goes into the normal orientation. But you notice that for every single one of these cases, there is a small range of frequencies for which it behaves anomalously. So that's the inference drawn from the first one, that the anomalous effect is seen for different primary particles and using the same secondary particle. Then let's go to the next one. Here what they've done is they've picked one of these, but they've changed the round, small secondary particles. And once again, you notice that it doesn't matter which SP you use, that for all of them, you see a set of values of frequencies for which B is negative, meaning that it's pointing in a direction that you don't expect it to. And then, of course, it settles into the normal orientation at higher frequencies. So in each of these cases, the trend is exactly the same. Now, you might say, well, maybe it's all got to do with the rod polymers and what happens to the rod polymers. Well, one of the things that they did to check that is they changed the concentration of the rods. So if this number is small, that means there are very, very few of these rod polymers. And if the number gets bigger, as the number gets bigger, you add more and more of the rod polymers. And one of these things you notice is if you scale the curves, all of these curves essentially lie one on top of the other. So that means it actually has very little to do with the rod polymers. It mostly has to do with the little guys. In fact, the behavior that the inference that you draw from this is that the anomalous behavior is actually each of these rods surrounded by a bunch of acolytes, which are the little small polymers. So this is important for us because what this tells us is we could actually build a model with a single rod surrounded by a bunch of particles, and that might already tell us part of the story. And that's exactly what we're going to do. And then finally, the size of the effect, which is given by how negative this becomes, depends on the charge of the primary particle. The primary polymer, if it's more charged it is, the bigger the effect. And you can see that it's bigger both in the negative direction as well as the positive direction. That means both the anomalous orientation as well as the normal orientation are affected by the charge. So now we're at the stage where we've talked about the motivation for the model that I'm going to tell you about. And based on their findings and what else is known about these types of systems, we can now put together the underlying assumptions behind the model that we're going to construct.